Okay, this is video number 2. So what's the angle of refraction when a light ray enters from air to glass an angle of 22 degrees to the normal, and n is 1.5 for glass. Okay, so what we have here, n1 over n2 equals sine theta 2 over sine theta 1. So remember here, this side n equals 1, this side n equals 1.5, light's coming in, bending towards the normal, angle 1, angle 2. So let's put it in. So sine of angle 2 is what we're trying to find. Putting in sine of angle 1, 22, and n1 and n2. So now how can we solve this? Okay, well, what we want this value here. So what you can do to get this one that's on the top line, so you must multiply everything else. Okay, so it's going to be 1 times sine 22 divided by 1.5 is equal to sine theta 2. So you can work that out, and you get 0.25, something like that. Okay, and then what you have is that's what sine theta is equal to. So we're running out of room here, we'll head up this way. So sine theta 2 is equal to 0.25. So how do I get theta 2? Well, what I do is I press the inverse sine button on the calculator. So if I press that first, so shift sine, and then your number, 0.25, and you get 14.5 degrees. Remember, always check that the angle is either decreased or increased depending on which way. In this case we're going into glass, so the angle is decreased. Now what is the refractive index? Okay, remember this is the value n that we've been talking about. So this is essentially a ratio of two speeds. Okay, you can define it as the speed of light in a vacuum divided by the speed of light in the medium. Okay, so that is your definition. Okay. Now, so for example, the speed of light in a vacuum is 3 times 10 to the 8. And what you're going to do is divide it by the speed in a medium. So for example, the speed in water, well actually let's say glass, is around about 2 times 10 to the 8. So what's the refractive index then for glass? 1.5. Okay, so all you got to do is you find this one by reference. Okay, you look up a reference and you get the speed of light, speed in a vacuum, and divided by that reference. So the 3 times 10 to the 8 is fixed, 2 times 10 to the 8 is your reference. So for water is almost 1, so it's be very close to the speed of light. So an example, let's do another one. Water has a refractive index of 1.3. What is the speed of light in water? So, the ratio then of the speed in a vacuum divided by the speed in water is equal to 1.3. So we want to find this one. It's on the bottom line, so we're going to get one of the ones at the top line and divide it by the other one. So it's going to be 3 times 10 to the 8 divided by 1.3 equals the speed in water. So what is that equal to then? Gives you 2.3 times 10 to the 8 meters per second. What we're going to do, we're going to do an experiment later that will essentially investigate a critical angle. So what happens is, if we shine a laser into this boundary here, so this is the boundary, it will refract away from the normal up this way. Okay. If we keep increasing the angle around, okay, so let's say we get to here and shine it in, then it would bend even more that way. Okay. Then eventually you can get to a point where as you shine the light in, it actually bounces, like reflection instead of refraction. So what we call there is the critical angle for total internal reflection. Okay, so this is the minimum angle for total internal reflection. Remember, the angle is always from the normal. Always from normal. Okay, now, so the simple experiment is you move your light rays around, move them around, and then you eventually get a point where the light actually travels along. So let's say it's about here. Okay, the light actually travels along the boundary. Okay, that is your critical angle. Okay. Examples of that. Some examples of that is a optical fiber. It's not a mirror, it's just total internal reflection along the glass. You have binoculars actually use prisms. Okay, so triangle pieces of glass. Okay, and it actually totally internally reflects inside that glass. So that's actually better than using a mirror. Here's an example of a laser in some water bouncing off the surface. Here you can see the image of the turtle up in the surface of the water, showing that the light from the turtle is bouncing off the surface into your eye. And a mirage is also caused by total internal reflection, in a sense, okay, or just refraction really. So as the light goes down towards the ground, it actually gets bent because of the change in optical density of the air, and it can actually get to a point where it actually starts reflecting back up, or bent back up, and so you actually see the image into the ground. That's not really total internal reflection.